What specific problem does the mixture-of-recursions more method aim to solve in existing transformer architectures, particularly around parameter efficiency and adaptive computation?
The mixture-of-recursions more method addresses the challenge of unifying parameter efficiency and adaptive computation in existing transformer architectures. Traditional models often apply a fixed recursion depth to all tokens, which fails to adaptively allocate computational resources based on the complexity of individual tokens. More introduces a dynamic routing mechanism that assigns token-specific recursion depths, allowing the model to concentrate computation on more challenging tokens while reducing unnecessary processing for simpler ones. Additionally, More employs a recursion-wise key-value (KV) caching strategy that minimizes memory traffic and enhances throughput, further optimizing resource usage. By integrating these features, More effectively reduces parameter counts, cuts redundant computations, and improves overall efficiency within a single architecture.
How does the proposed More method work? Illustrate it step by step, detailing how the routing mechanism operates and how it integrates with the recursive transformer structure.
The mixture-of-recursions More method operates by dynamically adjusting the recursion depth for each token during both pre-training and inference, leveraging a routing mechanism that assigns token-specific recursion steps. This routing mechanism consists of two strategies: expert choice routing and token choice routing. In expert choice routing, each recursion depth acts as an expert that selects the top k tokens based on a computed score, ensuring that only the most demanding tokens receive additional computation. Conversely, token choice routing commits each token to a full sequence of recursion blocks from the start, assigning it to a specific recursion depth based on its hidden state. The integration with the recursive transformer structure is achieved through the use of shared parameter blocks, where tokens can traverse multiple recursion steps, allowing for weight sharing and reducing the overall parameter count. Additionally, More employs a key-value (KV) caching strategy that selectively stores KV pairs at each recursion depth, enhancing memory efficiency and throughput by ensuring that only relevant tokens are cached and accessed during attention operations. This combination of dynamic routing and efficient caching enables More to optimize computation and memory usage effectively, facilitating adaptive reasoning tailored to the complexity of each token.
Can you provide a simple yet illustrative example of how the dynamic recursion routing and KV caching work together in More? Walk through the algorithm steps with this example.
In the mixture-of-recursions More framework, dynamic recursion routing and key-value (KV) caching work in tandem to optimize computation for each token. For instance, consider a scenario where we have three tokens: people, and drugs. The dynamic routing mechanism assigns people and drugs to undergo three recursion steps due to their semantic richness, while and being a function word is assigned only one recursion step. During processing, the router evaluates the hidden states of these tokens and determines their respective recursion depths. As people and drugs pass through their assigned recursion blocks, they generate KV pairs at each step. However, only the KV pairs corresponding to the recursion depth assigned to each token are cached. For example, people stores its KV pairs at all three recursion depths, while and only caches its KV pair from the first step. This selective caching reduces memory usage and improves throughput, as the model can efficiently access the relevant KV pairs without recomputing them for every recursion. Thus, More effectively combines dynamic recursion routing with recursion-wise KV caching to allocate computational resources where they are most needed, enhancing both efficiency and performance.
What empirical results did the authors report regarding the performance of More compared to vanilla and recursive transformers? How do these results demonstrate the advantages of More?
The authors reported that under an equal training budget of 16, 5e18 flops, the mixture-of-recursions More model achieved a lower validation loss and surpassed the vanilla baseline in average few-shot accuracy, 43.1% versus 42.3%, despite using nearly 50% fewer parameters. Additionally, when comparing performance under a fixed number of training tokens, 20B, More with two recursions outperformed both vanilla and recursive baselines, achieving lower validation loss and higher accuracy while using 25% fewer training flops. These results demonstrate Moore's advantages in computational efficiency, allowing it to process more training tokens within the same flops budget, and its ability to maintain competitive or superior predictive performance as model size and compute scale increase. Furthermore, Moore's hierarchical filtering and recursion-wise attention mechanisms contributed to significant reductions in training time and peak memory usage, reinforcing its practical deployment benefits. Overall, these empirical findings highlight Moore's effectiveness in unifying parameter efficiency and adaptive computation, leading to improved performance metrics compared to traditional architectures.
What are some specific limitations or challenges of the Moore approach as discussed in the paper? How do these limitations impact potential real-world applications?
The Mixture-of-Recursions Moore approach faces several limitations, particularly regarding the routing strategies and key-value (KV) caching mechanisms. For instance, while expert choice routing ensures perfect load balancing, it suffers from information leakage, necessitating auxiliary routers or regularization losses to mitigate this issue. Additionally, the token choice routing, although free from such leakage, struggles with balancing loads among heterogeneous experts, which can lead to inefficiencies. Furthermore, the dynamic depth models encounter challenges with KV cache consistency during autoregressive decoding, as early exiting tokens may lack crucial key-value pairs for subsequent recursion depths, complicating the system. These limitations can hinder Moore's effectiveness in real-world applications, particularly in scenarios requiring high efficiency and accuracy, as they may lead to increased computational overhead and reduced performance in practical deployments.
What future research directions do the authors suggest for improving or extending the Mixture-of-Recursions framework?
The authors suggest several future research directions for enhancing the Mixture-of-Recursions Moore framework. One potential area is the exploration of more sophisticated routing mechanisms that could further improve the dynamic allocation of recursion depths, possibly integrating additional contextual information to refine token processing. Additionally, they highlight the need for investigating alternative key-value (KV) caching strategies that could optimize memory usage and computational efficiency, particularly in varying deployment scenarios. The authors also imply that further empirical studies could be conducted to assess the performance of Moore across different model sizes and compute budgets, ensuring its scalability and adaptability. Lastly, they mention the possibility of integrating Moore with other adaptive computation techniques to enhance its reasoning capabilities, thereby bridging the gap between adaptive compute and latent reasoning.